All right. So all of you, thank you very much for tuning in. We had more than an hour and a half discussion with all of us, the steering committee, uh, like me, Christopher, then uh, Christian, Gerd, and Laszlo. We are totally discussing uh, everything, very important things for the conference, especially the schedule. And this essentially about we have gone over this as you may change a little bit. Christopher may change a little bit here, but essentially it will be like that. The speakers we have already there, like I mentioned last time. Fine, and then each speaker has their email address here, so you can contact for more information. Each speaker. We may change the pictures if necessary, but essentially that's it. The committee, like I mentioned, is essentially the same. We are steering committee meeting today. So all five of us were there. The schedule is where we have the big changes, adjustments. Uh, Essentially, we say that 9 to 10:30 will be Christian's keynote speaker, but we start with the master of ceremony will be Christopher, who will speak about 15 minutes about what the mission of the conference is and details of the conference and some aspects of the cost speakers, who we are, steering committee, things like that. Then he'll turn over the mic to me. So 9:15 to 9:30, I will be talking about uh, welcoming everybody and then what we plan to do and what the speakers are going to speak and things like that. And then I'll turn over the mic to Christian, who will then continue re-emphasizing our things and then continue with this talk. Then we'll have a coffee break from 10:30 to 10:45. And then after the coffee break, Gerd will talk on his uh, uh, electron mass. And the chair will be Christopher at that time. Then Laszlo will talk about another half an hour for planetary erosion. And then 11:45, 12:30, I talk about the superluminal things and quantum gravity. Then we'll have the lunch from 12:30 to 1:30. And then 1:30 to 3, Christopher will be talking on his anamorphic and galactic measurements. Then 3 to 3:15 will be coffee break again. Then 3:15 to 4:15 will be Emmanuel's talk on superluminal graviton, and he will be joined by Antonios Velamendes as well. And Christopher essentially will be chairing most of the conference, and I'll be chairing the rest of it. Uh, then we'll have a panel discussion, supposedly 4:15 to 5, but it could be the actual panel discussion with the questions and answers, which will include that with in the final 5 minutes, maybe vote of thanks. So I'll be chairing that, and then Christopher, we will be fielding questions from the audience, and then each speaker will answer the questions to the best of their abilities, and the rest of it will be offline or the further communication either through email or we'll have a special text session where we'll devote to this conference and then people can come in and chime in and talk more about it and ask for more clarification questions and then if they have some more takes and then advances they can do that. So essentially the conference will end at 5, then 5 to 6, I and Christopher and anybody else will clean up and turn over the conference room to the NH Hotel, who is hosting us, with whom we are the contract for the whole day. Then the conference ends, and then uh, from 8 to 10, we are the closing ceremony with the dinner. We plan to have a reserved restaurant with all of us meeting together there and completing that, including uh, who are the press or anybody else want to join us there. Welcome to join us there. Then social entertainments, general discussions. So essentially, the conference will close that day by 10 o'clock, completely closed. Then there will be a post conference, and we all plan to go. We all be staying there, all steering committee and other people. press and whoever want to join us. The next day, the city tour. Mostly it'll be hop in, hop off, and essentially we'll be going to different places, and then probably a small cruise also we may take. So we'll finish that. Uh, it's slated to be 6:50 or 7. Could be up to 8 if necessary with dinner and things like that. Small dinner. Uh, and then that again is done. Then after that, everybody is on their own essentially. So Sunday I'll be going to Geneva, and then go to CERN, the sightseeing there, and then the CERN on Monday. Spend the whole day there, and then I fly back the next day, June 3rd, back to the US. So that's the plan, my plan, and then Christopher will stay one more day here on June 1st, and then he may go along with Gerd and Christian for more to see, or by himself. It's up to them. In nearby places and have the time for themselves. So that's essentially the conference things. And then any clarification, Christopher will give anything more additional things. Thanks. Okay, Christopher.
Sorry, I was muted. So if you take a look at the contact page as well at the end.
Oh, yes. Yeah, that's something. Yeah, very important. Yeah, we want to talk about the contact. Yes.
So we've changed the email address there to TechNet Earth Global. So any correspondence will wind up at that email address. I don't know if you've been checking that, have you, Rajan?
I have not checked yet.
Yeah, see, that's what I was saying, because originally it was just to my personal email, and since I've changed it, we have to remember to keep an eye on that. So that's something to consider. We'll check it out anyway. But
okay.
And then if you scroll down, we have the location of the conference. There's the address, but in the actual map there, if you scroll up to the map, thank you. Now, if you zoom in a bit on the map, I don't know if you can click the plus button. Now, see, it doesn't zoom in to where the hotel is, so you have to go a bit to the right. I think if you move the map to the right, or is it to the left, or to the right, to your right. There it is. There, Hotel NH Budapest City, with the sort of a pink. Yeah, that's it. So I don't know why the map isn't great. It's not really showing where the hotel is. It zooms in on the wrong building for a start. It's close, but it's not exact. But hopefully that's enough for people to be able to find it. Unless you have an idea of
this is the one. This is the map.
Like, you see the way you have a red pin there when you pressed. It'd be good if the map had a red pin on it. I don't know how to. And even where you have this square that comes up and tells you the information, it's got 4.3 stars. Stuff like that would be good if it came up, but it just doesn't. So
view larger map, it says. So let's see what it is.
So if you could go share that, is there a way to click the share button, I think, and then go to embed a map. Embed, yeah. Click that. And that looks a bit better. So if you could copy that, copy the HTML, yeah. And then just either email that to me or put it in the private chat, and I'll upload that and see if it makes a difference. Okay. So you have to go back to StreamYard, isn't it? To go to the private chat. No, don't put it in. Yeah, put in the, yes, that one. Because otherwise people will be wondering why we might not even be able to get it from the, so if you paste it in there, that's great. Now I'm going to just I'll copy that and see if I can paste it. It looks identical to what I have though, so I don't know if it's going to make any difference really, but it's worth a shot, right?
Yeah.
Okay, so is there any other points you want to make? I don't think so. Like a lot of it is more.
Yeah. So
I
the
think
only question, okay, one thing I want to emphasize here
yeah.
is there is a donate, of course, registration, those who want to do. There's a donate button. Feel free to donate as much as you can. And we plan to have a t-shirt. Possibly, we have to talk with Laszlo also, a small, uh, medium, large, and extra large. I think that should uh, cover all the people. And then we want to put it on Amazon.com. So anybody who donates $100 will get T-shirt. $200 to two T-shirts free. So like that, it goes like that. So how much you want to donate? You can press the donate button, and then it goes here to Christopher, and then you can donate with the PayPal, which many people, including me, prefer, or you can have your own credit card paying that, and then in euros essentially, and you can add, how much you can donate. You can put that amount, and then
Okay.
that will help us uh, to really promote and then go further from the conference. So that's we always seek that, and also the cause of science and advancement. We want to get money for doing all that, and hopefully we'll start the World University virtual classes, things like that. So it will help students of the future and the public in general to have that. And then we also have the contacts page where you can contact us through this email. Again, I had to check that. Um, and that gives further information about the
Okay.
conference as well as what the mission will be following that. The conference is just first of its kind, just a starting point for us, and
Yeah.
we'll continue that. Um, like Christian want to do every year in Munich, we may do in New Zealand, for example, next time. So it's all up to
Yeah.
how things work out. So
Interesting.
so yeah. So
So
like
just remind us again, how much does the t-shirt? How much is it worth? The t-shirt will be worth.
I would say $15 to $20, but I have to check.
Okay.
Uh,
And then how much do people have to donate in order to get one of those?
$100 for one free T-shirt. $200 two free shirts like that. Or even $200 you may get more than two actually. You get two plus one, so you may get three. So like
Two
that.
plus one. Okay. Thanks for that.
Uh,
So that's interesting. And so you'd be working on the designs, probably based around the poster, isn't it? But which
yes.
poster? I suppose I could go if you
Okay,
want.
we'll go back
We
to
can look at the
poster.
poster, but before we do that, if you want to refresh the screen on the contact page of the website, yeah. Oh no, of the website. So that'll be that one. If you refresh that page, yeah,
Oh, okay.
and scroll down. There we go. That's better, isn't it?
Yeah.
We have the marker on the hotel. It's centered, and we have the
Oh,
information
this is
in
the
the
new
top
one.
corner.
Okay.
So
So I don't need this now.
that's
Okay.
working now. Yeah, happy.
Yeah. Control score to, yeah, that's it, right? Okay.
Yeah. So it's pinned,
So,
and we have all the information in the corner. That's much better because the other
yeah.
way we were kind of getting a bit lost.
Yeah.
It would be
If
very
people
difficult
are,
to find.
yeah, for airport or anything like that, they come one car, they can put in their GPS,
That's it.
and then it gives
Directions.
directions also, I think. The
Yeah.
directions, for example, from airport, Budapest airport. Which one is that? That's
The top one there.
yeah, Lisset. Yeah, Lisset International Airport, and it gives the direction. It says 38 minutes
By car.
by car. Yeah, about half an hour, little or half an hour 45 minutes. So it's not too near, but I think it's okay.
Yeah, pretty good. Oh, that's pretty good.
Yeah.
Okay,
I
so
don't, yeah. Yeah. So that's good.
yeah,
So
all
that's
this will have to be either taking cars or trains
right.
or buses to the.
Transit.
Yeah.
Yeah. Walking, cycling. Okay.
Well,
Even
I'll be
cycling is not
walking.
done.
Yeah. So, okay, so
Yeah. I,
4 hours and 44 minutes. It's a long time. Okay, so let's check out the posters then. Now we had the first poster, which I will have to download off. It was stuck on the cloud, and I couldn't get access to it. So if you go not to messages, but rather to if you type in my name into that will work. If you go to overview, 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 yeah, and then scroll down. So these are the new poster. I'm not so there's the
the
detail.
old one was really good.
Oh
So
yeah,
I know whether
you
you
can
should.
also go if you scroll up, keep going a bit. See public files and select those. Just hit, yeah, there's different versions there you can click on if you want to see some of the older versions. There's that version. And then there's another one, I think it's number 5, possibly. Or number 6 or 5. Yeah, click on either of those. Oh, there you go.
Oh, yeah.
There's that one. So, and I think the rest are kind of, they are what they are. Oh, yeah. So you see, so if you go back to my profile then, you'll see the other one that's the green one. If you go back to my profile, there's actually further versions that Laszlo's been working on with the painting that he has.
This one, you mean?
No, go back to my profile. Go back to actually click on my name, Mike. Go to the top, and then click there, and then go to research, and then scroll down. There.
This one?
Yeah, that's one. And then scroll down. Yeah.
Oh, yeah, I like this one.
Okay,
Maybe
see, the only problem with this one is I haven't put in the name of the hotel.
Oh, yeah. If we can add that, we can do the front of the T-shirt and the back of the T-shirt. You can have the front of the T-shirt possibly, and the other one at the back of the, either way, you know.
Yeah, that could cost quite a lot to print, though, because of all the colors. So you might want to look at that. That would be very expensive. Another thing that they often do.
Who can do it? Laszlo can do it, or somebody. I don't know.
Well, if Laszlo's able to do it, that's fine. I'll leave that up to you to work out with Laszlo, because he's into clothing and stuff, isn't he?
Yeah, I'll put in the WhatsApp, the steering committee, so whoever want to pick it up, pick it up.
Great. Okay, that sounds good. I'll leave that up to you guys, but I'm going to edit that now. Pretty much. The reason why I wasn't able to do it up till now was because it's on the iCloud. See, it's difficult for me to get it. I can't access it anymore for some reason.
Oh.
The iCloud. That's why I created the new poster, which was very controversial.
Oh, yeah.
What can you do? So yeah, for some reason, oh wait, hang on. Maybe I can access it through the Pages app. And if I can't do it through there, I don't know where I can do it. Because it's not on OneDrive, you know, the it's on an iCloud. Now there's a poster. See, it just won't let me open it. And when I go to the website, then iCloud.com, there's the options to I can sign in, and then there's the list of all of the documents that I have up there, but not all. I can't, like, if it's a PDF, I cannot download it for some reason, and so so it's difficult for me to get things off iCloud for some reason. But it'd be nice to be able to edit that because I don't want to start again from scratch.
Yeah.
Pages. Here we go. It's loading. So I've got different. Oh, there it is. Can I download that? Download. Pages format. Okay, this is working. I think.
Good.
Creating a file for download. Preparing file. So maybe I was having, yes, okay, we got it. I'm going to rename it poster 1, and I'm going to, usually I'm saving everything where the website is saved, which is it's just the way I'm going about it. Keep everything in one place. Where's, oh, there it is. And I'll save that. Yeah, there's been a number of different, well, Laszlo has other versions of the poster, but you'll notice that the new poster has a lot more text in it than the older one because it has all of the references included, and that just wouldn't work on a t-shirt. You know, all that fine print will just become lost. So this
will be much easier, right? A little bit easier, maybe.
Oh yeah, just the other posters, much bigger text, and
yeah.
But I mean, we can discuss that with Laszlo. He can decide, oh, I might prefer this design. I'll just remove all the text, you know, or, you know, the main text. And then we can kind of re-jig it. If he just wants one image instead of 4, which is what the current, the one we're looking at here has is 4. And also, I don't know the, oh, still not opening. Oh, no, wait a second. Yeah, I don't know if it's is there any copyright on them? Probably not, but I would have chosen images that are in the public domain. So, but I don't know if that covers t-shirt. 2 of the images are my own.
Oh.
One of the galaxy, obviously, I did not take because I don't own a massive telescope, space telescope. And then
this
the other
one is yours.
Yeah. 2 of them are, and then the one of the, I don't know what that is. Is that a palace in Budapest or something? That is public domain as well. So, okay, so I've got that open now, and I just need to find the original post, or not the original, but the remake poster that we did, because that has the location. That's the new poster. And the location. Oh, this is all in. It's all in. The new poster is all in Hungarian. So I need to find the address of our
Maybe we
website.
can have the front one English and the back one Hungary. I don't know whether that helps. But
oh yeah, yeah. Yeah, Laszlo can handle the translation on that, so that's no problem. Yeah. Okay, so I've got TechNet Earth Global Science Conference 2025, Friday, 30th of May, 2025, 9 a.m. Central European Time. And there's a little bit about it. Visit the website for more details. So I'm not sure where to put the address.
Venue, you can say venue somewhere here. Friday, you can put venue under 2025 venue, so and so, one line if it's possible.
That's a good idea. Right.
Friday.
We'll put location or venue.
Location or venue.
Okay. There we go.
Can I refresh now?
Oh no, there's no. I haven't uploaded it yet. I'm just looking. Okay. I'm just looking at that. I think we need a new line there, and I might reduce the size of the text or something so that it fits. That'll have to do. That looks okay. Hmm. So there's just not a lot of space on this poster for moving things around. Um, that will have to do. It looks okay to me. Maybe I'll make this bold so that people just make the date
Okay.
and time bold, so it stands out a bit more. Well, it
Sure.
doesn't. Maybe I'll change the color of the location text to blue, so that stands out. Oh, that's gone a bit, fades a bit into the green, so maybe more red. Oh, yeah, that's better, but it's green and red tend to clash, and they're very difficult to. They're actually quite hard to look at and read. So, oh, there we go. Yellow kind of works. You know what maybe I'll change this text to yellow and that to white, and then have the time and date also in yellow because I don't know, it just because it's already bolded and stuff. Yeah, I don't really like the look of that though, so maybe I'll change that back to white. Sorry about this. This is the problem
No
with
problem.
you make changes with posters. You know, one change it sort of starts to cascade, and before long you have a completely different poster on your hands. You know.
Oh, yeah.
I don't really know what to do there. I'm sort of stuck in terms of. Maybe I'll change that to yellow as well. That works. I think that's the best I'm going to get. And then I'll save that. No, I'll export it to PDF. Export. Next. Now, the size of this file is going to be quite big, so you won't be able to view it on... Oh, shit. Sorry, excuse the language. I was trying to replace the poster that already exists. So I'll change that to 2. Export it. You know how if a file is exceeds a certain size limit on ResearchGate, it will say click to view file. It doesn't give an automatic, and that's not too good. We don't want it to be a click to view situation. So I'll just check if that file is going to be over the limit. So I'm going to have to figure out a way to compress it before I upload it.
Okay.
Yeah, it's 7.5 megabytes, so that is over the limit. So now I did have a way to compress PDFs using, I think it was Adobe, but then they started asking me for like money to do it or something. So I have switched to a different thing. I mean, technically, I should be able to just compress it on my own computer. Because some of these free ones are not that great. They don't tell you what the new size is going to be. They're not until you download it, and then you find out. You know, maybe it compresses it too much, and everything gets very grainy, which we don't want. So let's see what we can do. If this doesn't work, I'm going to have to switch to maybe using like, I don't have Photoshop on my computer anymore, so I might have to use. Oh, that's kind of good. I think searchable only for scans. Usually it gives you the option to compress it like a lot, a little. Oh, there's high compression. The lower the quality, the smaller is the file size. We want high. What happens if we change to high quality? Oh, okay. So it's not telling me what the new file size will be, which I don't like. So the whole point is to find out how much we're compressing it by. Start now. Okay, go. Some of these free sites can be very annoying, actually. A lot of advertising and stuff. Go better quality. Yeah, you see, they compress them seriously from like 7 megabytes down to 646 kilobytes. So that's, I'm
That's
guessing.
a lot.
Yeah, I'm guessing that's going to kill all the detail in those images. So that, like I was saying, the Adobe one was just a lot better. So I'm not going to. I might be able to use. Have you know this free imaging editor software called GIMP? That would probably be
What
the.
you have to do is shift this text a little bit down, all this text, and then put
Oh no,
one in
I've
between
already
two.
done that, Rajan. I've already edited the poster, so
Okay.
that's fine. It's just the size of the poster is too big for ResearchGate.
How did this one come in, though?
Well, I compressed it,
But
so
this
that's
seems to
why.
be fine.
So yeah, it's fine because I compressed the file size using Adobe. Remember I was saying that?
Ah,
But
ah,
Adobe's now asking for, I could start a free trial with them or something, but
ah.
I'm just too lazy to put in all my details and stuff. So I am just
Okay.
going to use the image editing software on my computer instead. I
Okay.
just need to find the file through GIMP, and I'm not that familiar with how to compress files using this software. It's a bit of an annoyance. Hopefully this works. Import. I guess we just import it all. Import that. Oh, it doesn't really want to import. Oh, no, it's just taking its time. And the resolution is 100 pixels. So it says anyway. Okay, let's see what we can do. I mean, it would probably be more interesting for viewers here if I could share my screen, but at the same time, we should be finished here quite shortly, so I won't bother. Okay, so we have some options. There's print size, scale image. I think we'll go for scale image. Now it's saying resolution X and Y in pixels. So if we reduce that, let's say 7.2 megabytes is 100%. Or this is not percent, is it? This is pixels per inch. So let's try that. Seems to have made no difference. Did it do anything? File, export as, we'll call it poster 3. Still not really seeing any file sizes, which that's what Photoshop will tell you the file size always, which is nice. But GIMP doesn't have that either. But it does give you a lot more control on what you can do. So it's now 2.5 megabytes, so I think that's pretty good. So I'll upload that now to ResearchGate. I also might change the conference, TechNet Conference Budapest, Hungary. That's a pretty good name, isn't it? Okay, so I'll just upload the new file. Oh, I need to do that, you need to go into public files and then go add a file. And then I'll go select to upload, select and upload, select and upload. And then back to Back to the tags and find a new poster and hit open. Oh, did that work? I don't think that worked. Oh, sorry, I'll have to do that again. I must have add file, select and upload, open. Yeah, I double clicked. So add only a public file I've reviewed and verified. Upload. I'm not going to notify anyone. Close. Yeah, okay, image quality is down a bit too much. But you can refresh the page there, Rajan, and you'll see you can see the difference.
Oh, location, okay. Budapest country, Friday, 30th May. Can you make it bold, the yellow one?
What do you mean more? Sorry.
Bold. Bold
It is
letter.
bold. Well, the date is bold. The location is not bold because I don't want.
Okay.
I kind of want the date and the location to be distinguished a bit from one another. Now, so that was the best.
Okay.
That was the best I could do.
Okay, that's fine.
Because the background is green. If I change it to blue, it fades into the green. If I change it to red, it becomes unreadable. So that was, and if it's white, it just doesn't stand out. It blends into the title. So that was the only solution that
I will share it. Hold on.
Oh yeah, please do. Yeah.
Share as a message. I'll send to you. I don't know the others. Christian. Emmanuel also here. Good. John, I don't know whether they. Maybe send to John.
Yeah.
I've not talked to them yet, but good. I kind of mentioned to Manuel that.
You mentioned what, Emmanuel? Sorry.
Yeah, about our conference. Of course, he's not able to come or anything, but.
Oh yeah, but he is.
John.
He knows about it, doesn't he?
Yeah, but he's not able to come, of course, now. But I'll send to John. I'll probably send a message to John, see how he's doing, and
yeah.
And who else is there? Okay, let's share that first. Okay, who else is there? Laszlo. Laszlo, of course, had to be there.
Okay, great. I got that. Thanks for sending that on.
Okay, when he sent to last week. What happened last week?
Let's go back
I think
to.
all of us have that. Yeah, so all of us should have this. All the steering committee people, yeah.
Yeah, I have to say that even GIMP, when you compress it with that, you lose a lot of the detail. So what I'll do is I'll just send That's fine. I'll just send you the if you're going to make a poster out of it, I will have to send you the original file. Don't use the one-off.
Yeah, can you put it in the WhatsApp?
Yeah, no, well, I'll email it to you. Is that okay?
Yeah, but we have to put it in the WhatsApp because whoever is doing the poster needs that.
Oh, actually, yeah, I can email. Yeah, that's fine. I can put it into both. I'll email you as and
Yeah,
then
yeah, both. Yeah, you can copy me.
yeah, you can just copy it
And
into.
then what we are the person who is doing the T-shirt had to figure out whether they can fit the whole thing together in one page or front and back, and also the back possibly in Hungarian. You know that last row can put. These are the decisions that the poster, the whoever is doing the T-shirt had to do. How easy to print this one.
Mhm.
Sometimes it's easier to print on one side just the graphics, the other side the text. It depends on how the T-shirt and how much it costs, things like that.
Okay, I see the problem now with the compression. When the imaging editing software was importing it, it
Uh-huh.
its default import was 100 dpi or something like that. So,
Oh.
which is a lot lower than the actual image. So that's why I wasn't able to increase or increase the. Yeah. Anyway, that was the problem. I don't know if that makes sense, but um. So I had to solve. I need to find out the original DPI of the image somehow, and then keep that um, for for the for the actual when I do the import. So let's try get info, size, resolution. Sounds like resolution should be DPI. Says it's 842 times 1191, which that sounds more like the actual dimensions of the image, though. So
Mm.
I was to open that in preview and go tools and where's just size. They won't let you just the size of the of a PDF in preview for some reason. It's a bit annoying. How are you supposed to compress a file in preview? I did look it up, but it had, it was giving me like advice on how to do it, instructions, I should say. But so it was like, oh, highlight, select this option and select another option, but I don't have those options on my computer, so it was completely useless. Must have been for a more updated version of Mac OS software or something like that. So this is not that easy to do. I'll just have to re-import it, and that'll be with a higher DPI. And the problem with that is I don't know what the higher DPI should be. Resolution. Well, if 100 was 2.5 megabytes, then presumably if we go up between, if 100 is 2.5, then 3 times that. So if I go 250, it should be okay. We shouldn't lose too much quality then. Import. So what's your talk about, Rajan?
Huh?
What are you doing your talk on? Seems like you're covering a lot of different topics.
Oh yeah, and I have a brief thing here. Maybe we can go through it. And then at some point, I like to, you know, have everybody, especially you, to go over that. So I have a lot here, but I just skip through. I mean, these are just basic, so I can skip through this here. I thought I can probably remove some of it, but the main thing is here. Supernal content says ODP. Uh, okay, it's part of the speaking. Um, Start with the abstract, which shows how it all started, dawn of physics, how the physics started. And Socrates was the first person to introduce the idea of philosophy of inquiry, what, why, and all that. Then Aristotle came with the metaphysics. Then Thales, it seems that he's the first physicist of Miletus. Water is the essential substance of all matter. Pythagoras, as we know, theorem geometry.
Mm.
Uh, so here, what I say is that what we go in theory is that we get a mental picture and we abstract that picture of the whole nature and universe, what we see. We see the earth, we see the night sky, space and time. So this is, I used even my electrochemistry, the subtraction to come up with the model. And that's how you get. So everything goes in and you come out like you have your hyperspace, the 4D and things like that comes out, right? It's like a
Mm.
revelation type of thing. Uh, then mathematically, we want to see that how well it fits into that. That's where the mathematics come into picture. Then the Quaternion, where we see that the Euclidean is not enough. So you have scalar, vector, and tensor operation. So I briefly will talk about that. And then the introduction. So explore the concept of superluminal theoretical foundation, implication quantum mechanics. Then the hot PDP mechanism, potential for understanding behavior quantum systems. So that's the first one. And then what are superluminal condensates? Are hypothetical quantum states of matter exhibiting effective velocities that may exceed the speed of light. So they challenge the conventional understanding of quantum mechanics, but they are not in violation of relativistic principle. Uh, you know, they don't involve mass or information moving faster than light. So hence that will not really contradict relativistic principle. The velocities emerge from collective behaviors like Bose-Einstein condensates or superfluids, essentially. Quantum field theory as well as condensed matter physics, the basis. So the first one is where I started. So like the superluminous phase that we have our in our IR mark list, the first one, theory of superluminous in the physics astronomy. So that's where we start from. So this is picture that Emmanuel has also put along with my thing. So luminous and subluminous phase, how they look like. So we are different phases. The multi-phase, so multi-phase universe, your superlunar phase we cannot see. Then the vacuum where it holds the speed of light constant, and then subluminous where it is below speed. This is what we are in. This is what we can see. Uh, so that's essentially what it is, vacuum space. So then we move on to theoretical foundations for that. So it'll be easier to wave group velocities, exceed the speed of light without violating relativity. So we do to do the to the matrix, we do Helmholtz decomposition. So the point tensor generate is understanding the quantum system energy transfer. So how does that work? Uh, this is the main thing. So Helmholtz decomposition, we have the rotational field and the gradient field, and then we have the upper and the lower aspect uh, of the tensor, and that gives the 2 by 2 matrix, which is the fundamental. So 2 by 2 Dirac type matrix, that's equivalent to this tensor, the Ket and the Bra tensor. And then we process this mathematics that's in this paper, and we get that's essentially what it is. So we get the wave functions and things like that. I'm not going to go. Then we talk about the hot PDP mechanism. Uh, they make speed analogous superfluids. Uh, there is a rank 6 tensor time wave function that comes out of that. I'm not going to go into details about the actual transformation equation. Z-Dynamic transform is highly complex. I mean, it's there in the paper. Many other papers that I'm listing here, the references. But I'll briefly mention what this rank 6 tensor is. Gravitational fields interaction is crucial. Geodesics, the motion of particles in the system shaped by geodesics. So how the geodesics are formed, it's a combined action of the gravity and time that I'm going to talk about. So the schematic PDP is this way, that you have the monopoles, south and the north pole, and the positron electron. They all form like a circuit, and they flow around, uh, and they create this vortex and the gradient. So that's how they start. Within a supernominal thing is everywhere homogeneous, a faster than speed of light. But within that, this distortion occurs because in the supernominal phase, you have both the south pole and the north pole, the monopoles are acting, but they start grouping together. And when they group together, they start raising the energy sufficient to produce the electron positron partons or quasi particles, and they start creating. It's like a nucleation process, any nucleation process, and they stabilize and they start forming the PDP circuit, which has a wave function given here. And when you do Coulomb Hilbert space, then we can convert to something like the Higgs boson mass and also the Coulomb gauge. So we have both the mass as well as the field aspect coming into the picture, and this is there in the paper that Christopher and Manuel Hamiltonian is more into detail, goes to the analysis. And in that analysis, we pick this one to be the possible scheme that explains how it works. So you have the North Pole, South Pole, and the electron and positron coming here. They come together and form a dipole magnetism, which is the Hode that John Hodge has proposed. So they form the dipole and they lock in this structure. So then once this is formed, the structure is locked in and the nucleus is formed. Now it starts to become, because of this locking mechanism, it keeps the speed of light constant and forms the vacuum phase. And then this particle will pop out of this vacuum, and then we have the formation. So this is one way to measure that in terms of experimental way to measure the sound and the light aspect. So we have this light and the sound tensors are perpendicular to each other, and you can measure using the oscilloscope and microprocessor that is uh, the piezoelectric measurements. That is there in the next paper with the Emery Taylor theoretical to experimental thing. So we are trying to measure whatever is possible. That's one thing that from the abstract theory to the experimental aspect is what is emphasized here. The time quantization in this context of quantum gravity, time itself may be quantized. That's the idea. Uh, that time forms after the PDP mechanism is formed. And then I also produce recently I have published this one. I'm going to put it in the research gate, and it's in the final stages of correction, some correction, but the PDP is already available about spin spectroscopy, where I can show that we can actually figure out from the spins and E over M versus the spin that we can figure out about a graviton, how it acts. And I will show you that picture little later. So energy temperature equivalence. Spin spectroscopy allows for experimental verification of signal to noise equivalence. So we want to connect continuously the physics. We develop the theory, the model, but we have to also measure it. We have to find a way to experimentally measure. That's want to emphasize that. That's very important because a lot of it may be lost in the mathematics, like the string theory, but we have to, we cannot get bogged down the mathematics. But the mathematics is important to find the quantitative aspect. So this is the rank six tensor group theory. So a rank six tensor can be written in this form: the time tensor in terms of a metric, and then the derivative of the Euler angles of rotation with respect to uh, domains uh, uh, of space and time, for example. So and then domains of reality in general. It's typically that's space and time, but it could be others. So it's a general formulation that helps that. If the some a lot of times the metric is equal to is unitary, we can take it as unitary, and then we can express it a simpler way. That's there in the quantum gravity paper that I have given. Uh, and then that all comes together. They can describe a physics wherein you have this condensate, and this condensate is split. So it splits into uh, in a quantum form type thing, a 0 point thing, and also micro black hole. So that's the original theory as we see here. Originally in the matrix, you have the 0 point and the black hole. So they split into that, and then we can also look at how the waves, in terms of waves, that these are longitudinal waves, but at the local level, the hot PDP mechanism, you have the vortex forming. That's how you create this point singularity, and from which the micro black hole that starts growing to a larger radius. And then, like the Gertz talk earlier pointed out, maybe we are living inside a black hole. That's a possibility. So, but this shows about the quantum level. Quantum level, there is a micro black hole, and then that creates the gravitational wave, and this 0 point creates the cosmic wave. These are all micro level things. So now you can use the geometry uh, to in terms of signal to noise ratio as well. So you have a noise. The superluminal phase will be essentially noisy. So we cannot really measure, we cannot see or anything, but it'll be noisy. But out of this noise comes the signal. So you can, from the hot PDP mechanism forms, it starts creating the signal. It has enough energy that it starts to have this with the resonance, it creates that energy. So this is the equation that connects between noise and the signal. And uh, I mean, on the advanced level right now, I'm considering about the functors. So the noise and signals are functors, but they come together and they form functional things like that. So that's the overall theory that eventually will form out. And now we can convert from Euclidean to Riemannian geometry using these type of relationships. You can convert Euclidean to Riemannian. So Euclidean x, y, z, and then theta into phi, alpha, beta, and then we can convert to Riemannian type uh, tensor that many people have used, including Einstein and Bohr, everybody.
Mm.
So this is a spin spectroscopy. This is a snapshot of one of the main results of the spin spectroscopy analysis. So you are essentially charge to ratio. It's a fundamental E or M from Rutherford. Electron to mass ratio is the most fundamental uh, parameter or variable or the data that's available. And then that's plotted against spin. So it's a classical thing versus a spin, which is quantum. So we are really using how the quantum theory is modulating the classical theory. Essentially, that's all it is, because they are all connected. Um, the spin of the fermions, which include electron, positron, and all, and the bosons, which includes photons, especially, and the gravitons, which are spin 2 particles. So how their relationship and what changes are these aspects are the Thomas precision. We know that's the fundamental thing because of the magnetic Bohr magneton and the Bohr magneton. Uh, Even the classical physics, we have this precision uh, and of the electron because of the magnetic effect. Then the Bohr magneton separately will have an effect, and Compton electromagnetic effect because of the wave aspect of the electron. So you have both the particle aspect and the wave aspect coming together of the electrons, and they change this relationship a little bit, and that should be measurable. This is the idea uh, of measurement. So if we can measure this slight deviation, for example, with LHC or something, in the LHC, use this spin spectroscopy, we can actually delineate between electron, positron, Higgs boson, and graviton. We can see as an indirect effect. We may not see a direct effect of the graviton with spin 2 because it's much higher. Right now, it needs much higher energy than the LHC can give. But so it could be way below, and it's still a theoretical particle. But the graviton can be interpreted out of this spin spectroscopy that if it shows up there, we can show that there is a graviton here. So if we see the near the two, some measurements that will correspond to graviton. That's the idea of the spin spectroscopy. So if we see these, we can measure and then see that this is corresponding, and that will be a good experimental evidence of the correctness of these theories. So that will help to unify for a very important step towards quantum gravity. Uh, then I am going to go into detail. I just want to bring out this one. I am going to go into detail. But essentially, you can use the signal to noise algorithm to find out about the noise and then uh, about how the end states, the two end states of the universe, uh, with the maximum signal as a vacuum, uh, unitizing this one, we can find the temperature. So when the temperature on one side is superconductivity, the other side is the vacuum aspect. So this is how the universe forms. So the two sides of the temperature entropy aspects. And there's more in this paper. I give more details about that paper, and we can discuss that. It's a very important result of the end states of the universe, but that's something we can discuss later. So this is a typical kind of a signal that normally we could see, a spectral power density. If somebody uses any kind of monitoring technique, this is kind of a signal that you would see, and we can. I have done a Python program to do this, and how they can delineate the CMBR, which is the cosmic microwave background, like I talked about, from the 0 point, and the gravitation wave, which is the micro black hole, interaction that creates the gravitational wave. So we can actually figure out that when you put it that, and then we can say that the M brains and everything have come together. So we have to analyze this signal in order to figure out the main aspect. And this is in this paper. Many of them are covered in this paper. Signal to noise measurement. That's the main aspect. And then some application is scalar equation under gravitational field. So we can define action based on this uh, and represent the gravitational mass. So you have inertial mass and gravitational mass, and the quantum gravity time tensor, how they interact. This is and we can get a Lagrangian of Lagrangian is the equation of motion from the action and the time differential. Then with Christopher done the 4D toroid hyperspace. That's something that's going to happen next. Okay, scalarizing. I just want to show this as again this crowded place. But here, essentially, you can scalarize tensor by using this flattening of tensor method. So then we can express this Francis tensor in terms of a simple vector time, and that's the Bra vector. Then the Keck vector will be the gravity equal gravity aspect. So the gravity becomes these one, and they are connected by some scalar field. So they come together and they create the real scalar time and gravity coming together. Very similar to uh, the the matrix that Schwarzschild uses. This is a Minkowski space time. So we can all reduce to that. Uh, it becomes like a Schwarzschild matrix. So there is a connection. I come from the abstract side and show that we can convert to a Schwarzschild matrix. So they are consistent with that. Uh, so stress and mass, also how the gravity itself is acting is a real puzzle even now after Galilean thing. Nobody is able to really pinpoint how gravity comes to picture. This idea of quantum gravity is to explain that aspect. And the mass aspect, the mass tensor we have, uh, how it connects with wave, the wave function. So they interact and they produce a scalar mass called a gravitational mass. And that connects with the original mass is the inertial mass. When they connect with the wave function, they make the gravitational mass and they interact together. And that's how we get with along with the time, the actual effect, the actual scalar effect we see. Then we can make a very simple Lagrangian. It's a function of uh, this gravitational mass, the time, quantum gravity time, R, which is the 4D toroid hyperspace that Christopher is going to talk about, and we are going to try to apply that eventually. Uh, so this is a simple problem sorry uh, that shows how we can simplify this into a Newtonian type thing, which all the theories try to finally explain in terms of the Newtonian classical physics. It's very important because that's the most measurable aspect. The scalar, we can measure in a scale, in a balance, we can measure the mass, we can measure all that. Except really, people are not being able to show the gravitational attraction in our system. So that's still a puzzle. Nevertheless, the Lagrangian, the whole calculation here, I'm not going to go into detail here. Lagrangian, you can apply for the case of Newtonian, simple Newtonian in a gravitation field. And when we do these calculations, we can show, you can see how simple A becomes minus G or A plus G is equal to 0. A is the acceleration and G is the acceleration gravity, the gravity, which is 9.8 on Earth meters per second. So this is the equivalence principle. And you can see that when you analyze that, we can show the simple harmonic motion. And I have a simple experiment to show that if you put in a closed chamber a simple ball hanging from a thread, pivoted, then after a long period of time, it will start oscillating. This is what prediction is. So based on this theory of the equivalence, because there's superluminal thing, there's noise there around that, surrounding that, and that noise eventually, with the hot PDP mechanism, is creating the hot quantum gravity, and this quantum gravity is going to create the oscillation that we talked about, the gravitation micro back wall and the 0 point. So at the quantum level, they start acting and then eventually become the mesoscopic phenomena. So that's the idea that comes from this analysis. So 0 point theory again is a crucial role, and this aspect manifests in the cosmic micro. This is by the micro back wall aspect is turns into micro gravitational waves, like I mentioned before. So the implications are a novel connection between membrane theory and gravitational interactions. So the membrane theory, I'm not going to go into detail about theory, membrane, but we know that it's more than string theory. It's a two-dimensional aspect of the vibrations, and this two-dimensional aspect of vibrations connected to the gravitational interaction. So we have to mathematics is important. I mean, we have to eventually show that, and then we have to come up with the parameters which can measure them, and then only this theory is going to be valid, or any theory, for example. The microgravity gives as a signature of superluminous condensate using advanced gravitational wave detect, and the CMBR evidence of quantum gravitational effects early times of the universe. So these are some of the things. So conclusion is that explore the theoretical concepts, how they are interconnected, because the supernova condensates everywhere faster than speed of light. Then the hot PDP mechanism makes into particles, and the time condensation is the one that helps to create the separateness of the particles from the waves, and the quantum gravity connects them together at the small level and at the big level. And they, these research open real potential value for experimental verifications, nature of gravity, time, and quantum systems. Experimental detection of microvibration waves and study of EMBR will be pivotal testing the ideas. The understanding behavior supernova relation might lead us to deeper understanding of universe's fundamental laws. So this is the main aspect of the conference. I just want to okay. These are the conclusions. Then this is the main reference point. These are not the only ones, but some of them. It's a sample of the references that I'm giving here. Then I just throw out my thinking process in a way that how we come up with the theory. For example, uh, the theory of gravity is based on Galilean experiment. Then we have thermodynamics, which any talk, like you cannot cover all that, but these are the main aspects. Then we have ultraviolet spectroscopy that led the from the classical physics necessity for quantum physics, and also later on relativity. But relativity talked about module. The matter is the space-time bending that causes gravity. Uh, then, of course, we came up with the vacuum catastrophe between these two, relativity and quantum mechanics. So this goes on. So emergent theory, quantification of weak to strong nuclear, my electromagnetic gravitational gauge field matter. So these are things that's going on now. The physics requires anytime uh, observables. So we cannot just come up with theory or models, but we have to come up with the observables as well. And so there should be a way to prove that. Quantum mechanics stands out right now as the main thing with quantum field theory and everything, the standard model. The theory of relativity still are very quite active to describe the cosmic aspects. So the quantum cosmology is the main aspect driving now. And I am a quantum cosmologist now. So quantum gravity and quantum unifying efforts with theoretical physics. And I also do discontinuum physics with Emery Taylor, which I cannot present it here, but that's the area that talks about the graininess of structures and how they come about, how that is connected to the fine structure constant, things like that. We have advanced that theory very, very accurately. Uh, so the real aspect, of course, do we see in the real life these things? So mesoscopic observation. Some of the in one Canadian journal, I have pointed out how we can observe ducks and the swans and interpret them, uh, interpret these matrix things. So that's an interesting way. Normal eye observable measurements. When we see in the eye, how that connects with the quantum aspect, what we observe with our human eye. What we see, okay, what we see is what light is there. What we hear, what sounds that vibrate. So these are very simple things, but they can be connected to this thing. So observe what are the observables possible ensembles from the quantum theory. We can come up with the ensembles which are observable. This is how it is used to even prove quantum entanglement, things like that. Sensing space and time. Then you have different symmetries possible that I'm working on, the space and time, and they could be the fundamental aspect could be prime factorization, which makes the locally as well as globally two different symmetries. So the prime factorization with a magic square aspect, which creates a local symmetry, will upset the global symmetry, and vice versa. Then the global symmetries start coming up, and that upsets the local thing. So this dynamic keeps going back and forth between local and the global aspect. This is the idea. So this is what keeps it dynamic, continuous evolving structures that we see in the universe with galaxies and our star systems, planets, and all within the plants, the formation of light, the Goldilocks zone, things like that. So specific conditions lead to the understanding of human life and consciousness itself to some degree of the mind. Uh, so the experimental ways are parametric. We have to prove it by experiments. So you need equipment, instrumentation, and sensor and actuate. Sensors are we actually measure what it is, very low level signal, and the actuators they're actually like motors and things like that, which will activate the thing. Um, then gears, measurement gears, graphing techniques, programmable algorithms, emergent tabletop experiments. There are a lot of tabletop experiments which are generated. Emmanuel is one person who has done many. I have seen it in its Greek Hellenic laboratory, some of the laptop experiments to prove some of the aspects of these eventually the superluminal things. He's going to talk about that later. Laser holograms, hadron colliders. We know. I'm going to try to go there in CERN in person. I don't know how much I can see, but then space telescope that we see James Webb, for example, giving new understanding that we have to modify our theory about cosmology. Then the metrically cutting. So the metrics are very important aspect. Measurements. What is measurable? What is not measurable? Right? We know the scalar aspect is the important thing for measurement. Tensors normally are not measurable. So we have to convert them scalar things. Quantum microscopes that are coming up, mesoscopic light and sound, clock. Clock we use measure for scalar times. So the problems are limiting space, time, uh, human interpretable signals. So everything has transformed so that we can actually observe them or sense them. Resolution magnification very important in understanding that because everything else become like noise. Metaphysical measurements even a lot of it's measured by our thought process. We can measure some of it. The mind over matter with the quantum computing, artificial intelligence. Those are coming up. Uh, Quorum. So we want to create a quorum. You will have a panel discussion eventually, and we agree. We may not agree everything. We had debate about many things. Uh, why is physics key to understanding nature? So what's the role of the physics? Why is it important that we are pushing the boundaries? That we are talking in this conference itself. Questions and answers. That we'll entertain questions with people and try to answer to our best level possible. Um, and the literature, STEM education for kids that are going up from school to colleges. So they have STEM is very important. Science, technology, engineering, math. The typology aspect and the STEM education has become very important to understand all the things that's happening with robotics and artificial intelligence among them. So this is one of the things that I'm working on about the document movie uh, about putting together how the audio, image, uh, texting, video, coding, and communication come together. So they are all applying many of the principles that I talked about in this model. So they apply directly in the model aspects. To see, if there's time, I will explain these things. But essentially, the local system, like I talked about, how the local system, the global system interact, the signals interact, and create a time loop effect. I may not have enough time to go over, but we are in a time loop. 1960 to 2040 is one time loop. Specific things are happening. And after 2040, the global, that's the like a Halley's comet, will shift our Earth to a norm, uh, uh, new norm, like Earth 2, for example. And this is like a rider. Maxwell, how the Maxwell equation can explain some of the ball lightning that Laszlo talked about, and that's one of the puzzles or riders we can talk about. Uh, we'll discuss that whenever later on. And this is like a traffic map of the whole physics, how the physics from Bohr and Einstein, everything come together. And the documentary movie will use this some of it, how they interact and how the interesting aspect, quantum gravity, and things like that. This is the functor aspect. The North Pole and South Pole are in the superlunar level are functors, which means they are categories, just categories, but they come together because of the grouping effect. The random fluctuation brings them together, and they form like a functional, and that's how we get a hot PDP mechanism. And then this function will act. Then the function is actually the current flow, the actually flow once we establish the proper potential. So you have very high resistance initially, but then the proper with the proper grouping, we reduce the resistance enough for the current to flow, and that's how we get the real particles. So the finally, it is how I uh, have put together these things in one of the papers where we have the wave functions interacting to produce quantum density matrix. So this is essentially what it is. So this is essentially the whole thing. If you have any questions, I'd like to entertain your questions. Uh, so essentially, that's what it is. Okay.
Okay, good. So how long is that? When did you start speaking?
Oh, did I were you able to see that? I'm not sure.
Yeah,
Anyway,
I was able to see it.
able to see it, right?
Yeah.
Okay.
Uh,
So I had to see when did we start? Maybe like 45 minutes, actually more than 45. Okay.
that's
So I
okay,
had to
though,
reduce
because
it.
you have 45 minutes, don't you?
Okay. But then we have to have some time for question answers, right?
Oh yeah, that's a good point. Yeah, I don't think you
So
don't
I
have
had to
to.
find out. Yeah, I'll check how much time and I'll try to reduce some of it. But I will think, okay now for now.
Yeah, I suppose if you
Uh,
like, there's a lot of opportunity to reduce some stuff there. For
okay.
instance, you finish up with usually you finish up your talk with the references, but I noticed you went on with
Yeah, further. Maybe I can stop at that and then I can briefly just scan through and then say these are the additional things I'm considering, but I'm not going to talk about it. And we also interested further down in the text forum or something, we'll talk further about that. So
yeah,
can
because I
we
mean,
stop
well,
at
there's
that?
some. It sounds like you're sort of just briefly going over some projects that you have in mind, which is
Yeah,
interesting. It's kind of a laid back way of
yeah,
doing the discussion, I guess, which is there's no harm in that.
okay,
Then I mean, technically you start off with some discussion about at the beginning. You have a slide about sort of kind of based in the history of physics, which
huh?
it's about how like matter was different opinions on how matter was created. I think that's a good way to start a talk. Like I'm considering doing that as well. It's a similar
Okay,
kind of thing. Um, but I don't know. I think it's good. Like if it's but it might in your case it might not be like totally, if you were looking to, if you had to shave time off somewhere else, you could remove that. But because you can start, you don't need to go all the way back to Aristotle to begin talking about what you're talking about. But still, as a kind of a bookend, to start things, to introduce it, it is a nice way of doing it. So I wouldn't get rid of that until, unless
Or
you.
spend little time, probably like reduce the time, like 1 minute or something. Reduce the
Yeah,
time.
probably wouldn't reduce it by that much. Also, I did notice that you tend to go through the slides quite quickly. Like, is that roughly the speed that you're going to be talking at, or?
Yeah, but if I don't do those things and after the references, if I just scan through them, then I have more time for each each.
I think
Then I
so.
can
It'd be
spend more.
probably better to spend, because I just thought, to dwell on some of the slides a bit more and go into a bit more detail. Because one positive thing about your research, well, like, you're bringing a lot of things together: quantum mechanics, quantum gravity, general relativity, M theory. This is like a lot. There's like a lot of terms, which I think you don't have to bring up unless you're going to like explain exactly why they're there or something. But at the same time, so you could spend more time focusing on some of the research, maybe some of the mathematics. I don't know, but yeah, it's good listening to you. At the start, I was a little bit focused on trying to get I was still working on the poster for the start of that, so you might have heard me like effing and blinding in the background as I was trying to get the resolution right. So that wasn't about your talk or anything. But I was still listening to it. It's very interesting because it's nice to have all those different topics that you're bringing up all coming together. There's something, it's intellectually stimulating. But maybe don't go like, if you keep going on, like after the references.
Oh yeah. Yeah, the thing is, I don't want to emphasize on the math. I want to reduce the emphasis on the math and more on the physics.
Well, I think that's a fair point. Like, I don't think it would be a good idea really to go into a detailed conversation about mathematics during one of these presentations, because you probably lose the audience, and you're not there to educate them on how the mathematics works or anything.
And they can, go to the reference, and then if they are like panel discussion, they want more things. That's one thing I can say about that. We may actually point out panel discussions. They can bring out the questions. Now, of course, we can do only that many in the panel, but we can continue later, and we'll have a text session. That's also I want to put there, where we'll devote at least 1 or 2 text sessions for this conference, where people can come in and ask for more clarification of each of the speakers.
I mean, you watch these presentations, and they'll usually they'll put up the equations, okay, but they'll just say, and these are the equations.
Yeah.
Like, they're not going to go through them and explain them.
Oh yeah.
So yeah, no. So I agree on that front. I don't think it's but I do think. So it's it's difficult. I don't want to like criticize your thing. I think it's good. So in a negative way, I think it is good. But at the same, so it's not that I want you to go into more detail in the mathematics side of things. I also thought the way you presented and spoke about it was quite interesting. But yeah, it'd be I don't know, it'd be nice if you could like dwell on some of the concepts a bit more, go deeper into it, and really provide.
I can put the general transform, for example.
Maybe provide people with not the transform, because that's going back to maths, isn't it? So what I'm looking for is more of a, like a narrative description of what you're doing on a slightly more in-depth kind of level. Might be good, might not. So you'll have to make that decision. It's your talk, and but well done anyway. So a bit more of a narrative thing. I was thinking, just so that the concepts become more clear, or not that they're. I don't think they're not clear though. I'm not saying that they're confused or anything, but that like you know the way you know the way they say to
Emphasis,
when you
emphasis.
introduce more emphasis. So when you introduce your talk, you tell people what you're going to do. Then when you give the talk, you tell people what the talk's about, like what you're doing. And then when you give the conclusion, you say what you did. So you kind of say things 3 times so that the point you're making, like, so there's a solid point that you're making in your presentation, and that point people should know what that point is, maybe. And so I'm not sure, like, if you were to ask me, but I don't, but I'm sure someone else who was paying more attention there, who wasn't trying to edit a poster, might be able to say, in a sentence, what you were trying to say. And I think it has to do with the, it would be the quantum. So see, there's a lot of things though, so it's hard for me to pin down one thing that you're saying. So if you were to just put it into a sentence, what is the point you're making? Superluminal condensates. That's what I'm thinking. So there's this other universe, and then it sort of reduces down into this one.
Yeah, there is the actual universe is not measurable or seeable, but it's a superluminal thing. That's because it's superluminal. So everything comes from that aspect, and it condenses to this, condenses to the real universe. But that's always there. That superluminal is always there. It was always there, and that has all the elements that create a universe. But then, due to the fluctuations, random fluctuations, they create these particular mechanisms that create. It could be the hot PDP, it could be the Higgs mechanism. Hot PDP is more like a particle mechanism. Higgs mechanism is more like the wave aspect, I think, more like. And then
there is a Higgs particle as well, isn't there? But it's a field.
Then they connect to the Higgs boson. Right.
It's a field, right? The Higgs field,
it's a field.
Really, it permeates everything, and it's responsible for what? It's responsible for giving a certain amount of the mass to matter, like a very small percentage, but still very important.
The superluminal thing is a larger entity of that Higgs field.
What is
superfluid?
Oh yeah. See, it's an interesting one. It's kind of confusing though in a way. So like, if you have this superluminal thing, it's moving faster than the speed of light, but it's like it's all pervasive, is it? So it's constantly moving around. Is the idea?
So it's there everywhere simultaneously, almost.
Oh yeah.
Kind of like that.
Right. And so how does it reduce to
so it is differentiating itself. Like I say, it splits up into a 0-point field and a macro black hole. It splits up. It's like anything like water. You can split up. It's like water, but you can split up into hydrogen and oxygen, right? Under certain conditions. The same way, it can split up into the 0-point field macro black hole, and they form their own nuclei, and the stable, like we see the nuclei. Suppose you have a whole molten liquid, it can form a nuclei inside, and you put like a single crystal, and the single crystal then produces a stable nuclei. See, if we see the nucleation growth,
why not just say that why not just say that the 0-point energy field creates everything?
It doesn't have enough energy, but what happens is that suppose there is certain noise which has certain entropy, right? But the 0-point has lower thing, a lower energy level, but then it has to, the energy, if equal to that, there has to be some higher energy level, and this higher energy level is the micro black hole. So
that bit I don't understand. So okay. So but then you're saying, so if we were to take the energy of the universe, whatever, and then we just take away all the matter, and we're trying to get rid of all the fluctuations, what we find is, quantum mechanics tells us that there's always some amount of energy left, isn't it? It's like 1/2, and that is the 0-point energy. And that's
Yeah,
like a
that's
considerable
closest.
amount of energy. But as you said, it's nothing compared to, well, it's
Yeah.
nothing compared to the matter and the like gamma ray radiation that's coming out of stars and stuff like that, or the centers of galaxies. So I agree. So you're saying, so you have this intense amount of energy, the superluminal energy. It splits into the 0 point energy, which is the kind of
Mhm.
residual small amount, and then the remainder that's creating the rest of the universe. Then
Mm.
is all being um, generated by these micro black holes. You're saying so.
Yeah.
So those are the particles, are they?
Yeah. Yeah, they are the particles or subparticles or what I call partons or unparticles. They're called because they are not real particles like the electron and the positron,
Oh,
but
okay.
they are the primordial thing which can be called as an unpart. I think there's something called unparticles, something
Okay,
like that.
right. Yeah, I've heard this term partons as well. There's so many of those. Some of them are kind of theoretical uh,
Yes.
ideas. Maybe they come out of string theory. I'm not sure if partons are in string theory, but yeah, you can find some very funny. Is there the not the electrons, or it's not a graviton, but it's some sort of particle like that mediates the strength of gravity, and it's called a what is it again? A gravion or something? It's got a name very similar to
Graviton.
some other. Yeah, it's got a name. I think it's similar to the graviton, but it's different. Then yeah, okay. So it's pretty complicated. So those are things you could talk about maybe to like you could probably go more in depth into those concepts in the time that you have, and really sort of spell them out so that people know exactly what you're trying to say. That might be a good idea. So, but it is interesting anyway. So it seems like you have a superluminal level, then you have it splits into these two things, and then the second thing that it splits into must split into more things then to actually create matter. Is that it?
Essentially, the superluminous thing phase split into vacuum phase, which holds the speed of light constant, and the 0 point field essentially is in that vacuum thing. And
Mm.
then the subluminal thing, which
Do
is
you feel
created
though?
by
Do
the
you feel
micro.
that you would not have
Hmm?
to? Do you not feel that you would not have to justify those points there that you made with some sort of mathematics, or how are you justifying them?
0 point field. That in the mathematics, I say the 0 point uh, field energy, the field, right? Helmholtz decomposition that splits into 0 point field, which is essentially forms the vacuum.
Oh yeah, so that's your mathematical basis is
Yes,
the Helmholtz.
this
So let's
Helmholtz.
say you have your superluminal field, yeah. Now you're going to decompose that using this Helmholtz thing into a 0 point energy field and micro black holes.
Yes.
Right. Which is it? So in Helmholtz, you're decomposing the gradient from the curl. Is that it?
Yes.
Okay. So, but how does that? So in a superluminal field, do you have a gradient? Do you have a curl? Why not?
They
Why
are
not?
mixed together. They are mixed together.
Okay. Well, you're saying
They
that
mix together.
the curl is the 0 point
Rotational.
energy, and the gradient
No,
is
no,
the
no. Curl is the micro black hole,
so the
and the
curl is
gradient actually is
0 point.
yeah.
And how do you prove that?
That's the 2 by 2 matrix. Remember
Uh,
the 2 by 2 matrix?
yeah.
I
All right.
showed the
Well, a
two
two
by
by
two
two
matrix.
matrix. 2 by 2 matrix can be used to what? It can be used to show the energy density of a gravitational well. Isn't that right? Is that like the Einstein metric or something?
Yeah, let me show that again.
But and can it also be used to describe 0 point energy? I've never heard it used in that context before.
Let me go back here. Yeah, this stuff.
Oh yeah.
So this is the micro-backward thing. This is the 0 point field.
So the diagonal and the anti-diagonal, is it?
Yeah, and diagonal is the 0 point field. The diagonal is the micro-backward thing. This is the curl. This is
So
the
the
curl.
mass is on
This is the gradient.
the mass is on the diagonal or something, and then the
Yeah,
non-physical elements are on the other side or something.
yeah. The wave. It can be called the wave aspect. This is the matter aspect or the particle aspect, and this is the wave aspect. The anti-diagonal is the wave aspect, and the diagonal is the matter aspect.
Okay, and then yeah, I don't really follow all of that. I mean, I get what you're saying there, but notation and all, you've got mu nu. So the items in that two-dimensional matrix are actually more two-dimensional matrices.
Yeah, because you have up, clockwise. I mean, going up versus going down, right? So in tensor, you
Just
need both.
they are the sums of two-dimensional matrices, aren't they? Oh no,
There are some.
yeah. Okay, and then so that splits into two different. So you decompose that into two different fields. One is the matter,
Yes.
one is the thing. And so that is a superluminal. And how does that matrix tell you anything about the speed?
This matrix, we have to transform it to find the speed. This is just a field, but it doesn't talk of the speed of the field. That's
So
that's further analysis. That's further analysis by finding the time and everything. So from this we transform. Remember the general transform, which gives the time. From that time, so it is not a simple thing, and I wouldn't think that it will be that simple because it involves the whole circuit. The whole circuit of the whole universe, essentially. So
that's a cool idea,
that,
but I just don't know. Like, I'm not sure I follow you. I just maybe it's because the equations are a bit like it'd be nicer if you could show. I don't know. Is it possible to show this visually or something, or like how do you?
yeah, I want to see what you mentioned a very important point, and thank you. Is that's why I'm thinking. I don't know whether it's possible in this conference, but a kind of a simulation. You know, a simulation of these things we put together, and that will be more visual things. That a simulation put all this algorithm together and create a visual.
Okay,
The
could you
program.
just like using something like
Yeah.
I don't know, like material that already exists or something, and say, well, there is this shape out there describes what's going on, or something like that.
Ah.
Like I don't know. So how did you come about? Did you arrive at this through the mathematics, or did you arrive at it through a visual concept in your mind, or?
Yeah, it starts from here. You see that it starts from here,
The
but
rotation.
originally it's abstract. Yeah, it's abstraction. It's abstraction process. So it's actually mathematical, I would say. Because abstraction is a mathematical thing. So then it corresponds to physics. You know, it connects with the physics, like this one. This is a superluminal thing. Something is churning around, essentially,
So
right? The
would you
superluminal thing is something is
there's
like
a
superfluid.
priori, like you have no evidence that this object exists, this superluminal vortex.
Well,
You're just
in
saying
a way
a
that,
priori this exists. I have no evidence, but this, and so you're basing it on something that you don't know whether it exists or not. Correct?
well, Emmanuel's thing does prove that some of his thing proves this churning effect, the magnetic
Where
magnetons.
it proves. How does it? Yeah, no, like there's definitely a history to the vortex in terms of like Maxwell's.
Yes.
Yeah, so I'm not denying that. I'm saying you're talking about all right. Okay, so you're talking about a superluminal thing. So you're saying Emmanuel has done some work on superluminal. He believes
Yes.
in the superluminal aspect, but
Yes.
surely, okay, but that's the thing that Emmanuel is saying exists in our reality, and then you seem to
Yes.
be elevating it to a different universe and saying that thing creates everything. Is that it?
Yeah. I mean, this supernormal thing contains, the things that what does it contain? It contains all the monopoles, everything. Only thing is that it is not arranged. It's not organized. It's not grouped. It's not uh, separated into phases. It's all mixed together, like in ocean, for example, like an ocean, right? Everything is mixed together, but
Yeah,
the ocean
it's
from
like
it,
a
it get
unified field.
isolated.
It's a unified field, right?
Yeah. So ocean has everything in
It's
together,
not mixed
but
together.
everything is turned into.
It's a unified field, right? It is one.
Yeah.
It's its own
Yeah.
field, like a fifth
Yes.
force that is made from all the
Yeah.
other forces combined, and then it breaks down. But why? So,
Yes.
like, if it's going to break into all of these forces, that's okay. But right, so it has to break into gravity, has to break into
Uh-huh.
electromagnetism, and the strong and the weak force, and if you want the Higgs field. So have you demonstrated how it does that? Also, why does it do that? You need to, like, okay, you say Helmholtz decomposition, but
Yeah.
you can't just say can you just say like Helmholtz decomposition is the reason why it breaks into these different things? Or do you need a reason why the Helmholtz decomposition? Do you know what I mean? Like,
Uh-huh.
what is the initial thing that occurs that causes the asymmetry or the deunification of the forces?
Okay. So as it this is a churning thing, right? Continuously churning, right? So
Yeah, but
any
just
random thing.
what just Rajan. Okay, so usually when we talk about like you have a unified field theory, and then they say like the energy begins to drop, and then because the energy drops, they split or whatever. But I don't think the energy can drop in this system, can it? Because it's in a different universe where everything is continuously at a high speed. So that's not going to drop, which is fine. All this is fine, but so so it seems like you're saying that the breaking of the forces is not real, like it's an illusion or something.
Yeah, it is like the constants.
Okay,
See,
so if
right
it's
now,
an
what is
illusion, then what is causing that?
okay? So right now, what keeps the thing like a Maxwell equation, everything is the constants. Like the speed of light is constant, the fine structure constant, right? And
Yeah.
then you have the permittivity. These are all constants. But in the supernormal thing, nothing is constant.
Okay.
None of these are constant.
That's the real world, is it?
Yeah, that is the world that exists all the time. But from this one, which has all the constant changing, by the churning action, they create situation
Okay, so
where the
Rajan,
constants.
can I ask a question about can you answer that question or if you can't answer, just say I don't know, because that would be easier for me to
Okay,
know.
what's the question?
Well, the question I was saying was that the superluminal world is the real world, yeah, and then
Uh,
the breaking of the forces. So it contains all the forces unified, and then when it breaks into our universe, it the superluminal universe is still there, like superimposed on our world. So you're saying so the forces don't actually break because they are still there. So
uh,
then the illusion, like our world, then becomes an illusion because it's not a real symmetry. It's not a real breaking of the symmetries, or that's the wrong word, of the forces. The forces are still unified; they just appear to be disunified. So I asked you, what is the mechanism for that? Or well, actually, that's not. I didn't use the word mechanism, but that's what people would normally ask. But I asked, like, how? Well, I suppose how are you going to come up with the physical theory of an illusion? Is possibly one of the implications of that. Like, what is the physical if it's an illusion, then what is the physical? Because it's not real, then, is it? So how can you come up with a physical theory? You basically, it's like Maya. The is it
Oh
Maya?
yeah.
Yeah. So how are you going to come up with a physical theory about Maya?
Okay. So let me show you one of the
Well,
things
can you
that
answer this question though, Rajan? Like,
yeah,
have you thought about
for this I had to show here because I think it might give this is the most recent one. I have not put in the research gate yet. It's almost done, but I have to I don't know whether they changed it now. Okay. Let me refresh this. Uh, they may have changed some of it. I have to check. But this is where it starts from. This is a very general thing, very abstract thing. All we see is a signal, right? So finally, what we see for outer space, anything is some kind of a signal. That's all we see. What that signal signifies is the important thing. So this is the abstract aspect of the signal, typical signal that we see. But when we process this, some of it I'm giving this, we get this type of thing which talks about like how the dark matter may come into picture.
Okay, this is going
And
very.
this,
I think this is going a bit off topic. I mean, it's interesting, but I'd have more questions to ask about this. So,
okay,
so we need to go back to what we were talking about. Okay,
okay.
so Rajan, I don't think that it is possible to come up with a theory that is like a physical theory about an illusory process.
It doesn't still exist. I agree that we are working towards that because I look at the time aspect. You see that? But you have to bring in your space
No,
aspect.
there is an answer that you could provide here, Rajan, that I would find convincing, but it's not.
It's not
It would
complete.
ultimately
It's not a
not be.
complete theory
It would
yet.
ultimately not be a physical theory. It would be a philosophical theory. So, um, okay, so we're just going to have to leave that. I think. You have your vortex. You have this thing. So I just don't see how a Helmholtz decomposition into two different things is going to create four forces unless they decompose again. But I don't think you can do. Might be able to do that. And also, well, if it was going to decompose into two forces initially, you'd assume one might be the
Yeah.
electro weak force, let's say, and the other
Uh-huh.
one would be the strong gravitational
Yes.
force. Because then you'd have
Uh-huh.
two forces, and then those two break again into electromagnetism and the weak force, and the other one breaks into the strong and the gravitational force. I feel like I'm doing a lot of the work for you here in terms of the conceptual
No,
design.
we have to come together.
But
I mean,
you were
with
breaking
your
it
thing.
into you're breaking it into what's it called? The 0 point and the micro black holes. So 0 point could contain, it's like loads of particles coming in and out of existence, isn't it? So we could imagine there's weak force particles, there's charged particles.
Yeah. 0 point essentially a only wave.
We normally don't think of 0 point as a force, you know?
It's a wave. It's a wave. Just a wave.
I don't know. Yeah, I mean, I'm not even sure if I'd agree with that, but possibly, yeah, I suppose. And then, yeah, and then the other one is a micro black hole. So that's going to be, I mean, you could equate that with gravity, but at the same time, can you really like, it's, a micro black hole is a specific kind of thing that exists. You wouldn't put all gravity into the into the category of micro black hole, of course, which is what you're saying. It sounds like you're trying to put the force of gravity, or are you? Am I understanding you correctly?
Well, the gravity is not the primordial thing. That's the main thing. The
So you think
gravity
the
is an
micro
effect
black holes?
that's
Are you
created.
saying the micro black holes are more fundamental than gravity or something?
Yes.
How? How are
Because
they? How is it more?
they
Yeah. Yeah.
okay.
Go on.
The gravitons, okay, in the what exists in
Yeah.
the superluminal space?
Does that mean that you're also
Only
saying
thing,
that 0 point energy is more fundamental than the other fields?
yes.
How?
So from the superluminal thing, what exists? What does exist in the superluminal thing? That's the main thing. One thing is that they have the monopoles. They're going. crazy by themselves. North monopole is going one way, south monopole is going another way. Okay.
Okay,
So
but wait a second there. Now hold up, because you've got a magnetic monopole up here in this superluminal unified
yeah,
force, right? But isn't
yeah,
a monopole is magnetic by definition? So
yes,
there's a force already up there called magnetism. So
yes,
then you cannot say that this superluminal entity or ether or whatever breaks into magnetism and electricity because you already have the magnetism separated up there. So that doesn't
well,
work. Also, wait
the
a second. Also, then you are placing magnetism above and before the 0 point energy. So that means that magnetism is more fundamental than the 0 point energy. See, these are things you need to clarify, I would say.
okay. So magnetism, when we say magnetism, it is dipole magnetism. See, that's what I want to say. But this is not dipole magnetism.
Okay, but it's still magnetism, though, isn't it? Still,
Yeah, it's a magnetic field.
okay.
It's a
Yeah,
field,
yeah.
Dirac field. It's like a Dirac field. So essentially, can
You'd
be
still
called,
consider it a force, like part of the electromagnetic force or something?
yeah, but you can, like a Higgs field, it's Dirac field. Instead of the Higgs field, it's a Dirac field. That's it.
Sorry, what is it? So Dirac field. Well, isn't it the Dirac field equation? What define Dirac field for me? Sorry.
Okay, Dirac derived this existence of the monopoles, right? Uh, so the monopoles have
But what is a Dirac field? I asked.
a Dirac field is where the magnetic field, the single magnetic monopole exists by themselves, and they create a field when they go around.
So is that what the Dirac field equation is about?
Yeah,
Are you sure?
Dirac. Let's look into the what you call, go to one of the
Wikipedia or something.
Dirac field. Let's see the actual definition. We'll go from
That's
there
a good idea.
because
Dirac
I don't want to.
field equation. I thought it had something to do with Einstein and gravity or something. Like a
Okay, example of fermionic field is the Dirac field, which describes fermionic. Okay, the
okay, so
electrons.
it's a fermionic spin field, right? Spin on. So I don't think that makes sense in the context of micro black hole or monopoles. Getting confused. Okay,
Fermi
so
Dirac. Oh,
yeah,
let
maybe
me
you meant something else.
Dirac field. How does
Yeah,
how do the Dirac field connect with the magnetic monopoles?
yeah. Okay, so I think I think I get where you're coming from. I think it's a little bit. See, this is what I would like. I would like it to be more structured logically so that I can follow it. But what you've got is pretty good. I like it anyway. You know, it's very, like I said, it's a lot of interesting terms and it's quite
So
evocative.
you see that? Yeah. Here
Yeah.
it says that. Okay, let's look into here. Maybe magnetic monopole. Let's look at magnetic monopole. Is hypothetical elementary particle
Yeah,
and trying to connect with the Dirac field. It talks about.
I don't know. I
Okay.
think this point you're making is a little bit too fine for me. I'm not interested in like these little definitions about like if a name, you know, direct. This is not like what I'm looking for because I think we should be like higher above this. This is more in the details of like possibly even down to semantics at a certain point. But I mean, if this is important, this should be in your talk. You know, this is important to explain something. I guess should it be addressed in the talk? Those kind of things. So those would be my.
Okay.
I don't know, but I mean, even if you were to talk about this, I don't know if that would help me understand it. That's my worry on that. Yeah. So, but yeah. So those are some things to think about. I mean, we can try and dig into this all night, but I don't know. But it is interesting. I mean, there's interesting ideas there, and just not. I mean, on one hand, I'm seeing it as a kind of a philosophical theory that you could wind up with a situation where the creation of the universe is just an illusion, which is, you know, obviously an old idea, but you see how I mean that would be a philosophical thing, because if it's illusory, then there probably, you know, you're talking about the importance of observables. Like, how would we observe like, let's say there was the particle that generated the illusion or something. How would you detect that if it exists outside of the illusion or something, you know? Those kind of concepts. But I mean, it's similar to my work with the anamorphic perspective cosmology thing, because I mean, we can't really observe this hypersphere that I'm looking into. So it just you know, trying to infer the size of the hypersphere based on some other things like redshift and maybe angular diameter or whatever. So that's what I've been attempting to do, and I think I have an answer, but it isn't the only answer, and also it's not a very satisfactory answer in another way, because it appears that what it's saying is that most of the galaxies that are redshifted, like the ones in the Great Wall, so the ones that closest to us, are within you know, several million miles, or kilometers, which is between the distance between the Earth and, you know, or it exists within the distance between the Earth and the Sun. You know, so that would mean that the Sun would have to be a lot closer to the Earth. And then the galaxies as well, I get the size measurements for the galaxies, and they're only tens of kilometers in diameter. So they're like really small and really close. But I mean, you could alter that by just increasing the size of the hypersphere, and they would go further away and they become much bigger, you know. Mm-hmm. But I have no justification for increasing the size of the hypersphere to that size, you know, because well, I can go into it in the talk, but basically I have the redshift for all the different diameters of the hypersphere, and it goes up in a zigzag line like this. And I think you recall from my previous presentation on it, I just chose the minimum one that I could. But we said, we might as well wait until we see where the line hits the zero line. But when you actually extrapolate and go out to the zero line, it just flatlines. Once it hits the zero line, it just flatlines. And it doesn't completely flatline though, because there are still higher bands above that. But and so you can take measurements for all these increasing hyperspheres, but it just looks weird. And I don't know why they don't appear as further zigzag lines, why they don't go beneath the zero line and into negative or blue shifted territory. So that's weird. Maybe it's a problem with my mathematics, but I don't think I'm going to be able to solve it by the time the presentation comes along.
Yeah.
Way too busy with writing the PhD. In fact, I'll probably have to take a break from everything else just to focus on that until the presentation, or until our conference on May 30th. So that will be the.
That's fine.
I might be able to come back.
We can say when I start that it is like a research in progress, what we are presenting.
Absolutely, absolutely, yeah. No, we don't have any. I mean, some people.
I will just write it here. Here somewhere, I'll put a note.
Well, you do that a lot. I mean, you're talking about ansatz. You do like suggest that your stuff is theoretical, obviously theoretical physics. So, but Yeah,
Okay, this
like, so I
is
mean, I definitely have issues with the work I'm presenting. I don't have all the answers, you know, and I'm not entirely sure how to find them. But it's more part of it is, yeah. So you're exploring things, and that's good. But you also have to be very strict with yourself, and also honest with your um,
okay.
audience as to what you're
This
trying to
is
present.
this is research in progress,
Okay, and yeah.
ongoing.
And I think, yeah, so all good research is always ongoing, isn't it? And then even the
Yeah.
you know, the work I've done into the 120 cell, I think
Mhm.
that was actually pretty successful in a lot of ways. You know, that
Oh yeah.
that has that kind of came to to a satisfactory sort of end. But whether the
Uh-huh.
entire process to get to that point is legitimate, like entirely legitimate or not, I
Uh-huh.
don't actually know. You know, but the ending was good, and I think it the whole thing then kind of gives some window into the universe possibly and how it's structured, and that's good. And obviously, there's more work to be done on that. That could be continue to be developed to whatever point. But the bigger problem is the anamorphic perspective cosmology, because, excuse me, we're rapidly approaching a point where, you know, it's how to decide, how to come to actual definitive um, quantifications on the size, like the radial size of the hypersphere, and yeah, and just, yeah, definitively say. But I'm not there yet, and it may never happen. So, but it's still very. It's a lot of fun getting to this point anyway. But it'd be a bit
Oh yeah.
disappointing if, you know, it would be a bit disappointing if it couldn't get a definitive size on, say, like, oh
To
well.
emphasize that it's a research in progress, which means that it's not an end in, it's by no means an end. It's probably
No,
a beginning.
yeah, exactly. Yeah, yeah, I mean, Einstein, yeah, he did a lot of work, and then I think he on his on, like, he did a lot of work. He was like, I understand my theory, but then when he gave it to the mathematicians, he was like, I no longer understand the theory. And I think when he was on his deathbed, like, he was like,
The
so,
more you know, the less you think you know. The less you start realizing that there's more to know,
well, that's
kind of
true as
thing.
well. Yeah. Well, this is it. I
That's
mean, I
kind
think we tried to use Einstein's theory as the basis of everything. Then, you know, it became like,
yeah.
oh, because of the cosmological constant was in there, which
Uh-huh.
was, you know, maybe a bit dubious. I mean, obviously, it looks it looks good on paper from the Big Bang and space expanding, or even accelerating its expansion, which would require, you know, you'd have to alter the cosmological constant again. But that's not really very satisfactory. Like, oh, they find out, okay, the universe is not just expanding, it's accelerating. So this is a problem. But then they go, oh no, that's not a problem. We have the cosmological constant. We'll just change the value. That's like
Mhm.
not really a, you know, it's not like the theory is predicting that the universe must be accelerating, you know? So
Mhm.
so that's not like, in the way Einstein's like, oh, my greatest blunder was not putting in a positive cosmological constant. Well, why wasn't his greatest blunder not putting in a cosmological constant that proved the acceleration of the expansion, you know? And then it turns
Mhm.
out, oh, well, actually, the accelerated expansion was just possibly an error due to a low number of sampling of galaxies or something like that, redshifts, you
Mhm.
know? So now they're saying, well, maybe it's not expanding rapidly. So then they go, oh, well, it's fine. We just reduce the cosmological constant again. But they're not like learning anything. They're just like hiring and lowering a value in an equation. But then this whole thing, so they have that link to their entire universe model, implies that, well, it must be Einstein's equations or something that govern space even on the most massive scales, you know. And that, I think, is where they're falling down, you know, because they're bringing in de Sitter space, anti-de Sitter space, mainly de Sitter space, which doesn't actually even describe our universe, which is a problem, and also seems to be sitting somewhere in the future where the universe is completely died out in some sort of cold expansion. And then, of course, you have the entropic gravity kind of theories with the holographic universe and bulk space, you know, a holographic projection from the sort of, I guess, it's not the edge of the observable universe, although it could be, but it seems to be almost, you know, so you have this projection from the surface into the bulk space, and that's kind of like an event horizon then, which is connected to entropy somehow, and therefore to black holes and blah, blah, blah. And it all gets a bit, you know, so they're trying to like, well, we have gravity and we have Einstein's theory, and we need a big scaled version of that. So it seems like they're trying to shoehorn a lot of things in there. But I don't necessarily disagree with them completely, because, I mean, if you look at anamorphic perspective cosmology, we have the hypersphere, which is not the observable universe. It would be the entire universe. Like, so, but at the top of that, at the North Pole, is this like kind of like a singularity, and the very point at the center of that singularity does not exist in our universe. Once it's projected onto the tangent plane, it will always lie outside the universe. So there is those kind of similarities, nods, or acknowledgements to concepts that appear in Einstein's work to do with black holes and singularities. But I would say that it is also very different to it, you know. Because I don't think that, while I think space-time curve, because you know the way I was always doubtful about a lot of the precepts of relativity and such. I think over time I've, like, you know, I see that they don't have to be they don't have to contradict other things. They can work in tandem with them. And so I would say, like, that space-time curvature and all of that is pretty important. I think. I mean, obviously, if I'm right, which I'm probably not, but if the hypersphere is as small as I'm thinking it is, and the galaxies are that close, and they're very small, like tens of kilometers, then they're obviously going to be quite light. There's not going to be much mass in them, so they could rotate without the need of dark matter, you know. And then you could ask, well, how are they bending the light so much as well?
Magnetars. That's magnetars.
You think if you had these magnetars in these very small galaxies, they might be able to produce that level of what's it called? I'm sorry, space-time curvature, or you know, the lensing, the gravitational lensing.
Yeah.
I don't know, Rajan. Maybe, but anyway,
magnetars are very super magnetic field. They are much more than a magnetic field. They're huge magnetic fields, like toroidal, like we see LHC or any place like that. I don't know if even LHC can simulate that. The magnetic field is much.
Yeah. Well, that's it. So I mean, you can see my dilemma. Like, pretty much, you know, if these galaxies exist within the orbit of the sun and the Earth, like that distance, then that implies that the sun would be a lot closer. And there's pretty much only one group out there that are suggesting that the sun is, like, maybe you know, a couple of 1,000 kilometers away, or less than 1,000 kilometers away, that kind of area. And that's people who are talking about flat Earth, you know, flat Earth people. So, but they, you know, they make some good points in that particular area about maybe the sun is smaller, maybe it is closer. But so it just, yeah. So my theory kind of comes to the point where, or hypothesis or whatever, comes to the point where it's like, I don't know, you know, what's true, what isn't true. Sort of turns the whole universe on its head, and that's sort of I would consider that a well, that's fine. You know, not knowing is fine. I have no problem with that. But so I have this thing where if I'm doing research and I get an answer that's wrong, I'll just assume it's right, you know, because it's the answer I got, and then I go with that for a while until I find out, oh no, wait, that is wrong, and then I redo it. So that's kind of the way I'm approaching this presentation, is to say, these are my answers. The galaxies are small and very close to us, and therefore that's right, you know? But it probably isn't right, but it's, how do you prove it otherwise? So, yeah, like you say,
magnet powers
work in
can
progress.
have
Yeah.
can have
Magnet
to
powers,
10 to 15 Gauss, and then yeah,
okay.
10 to 12, up to 10 to 15 Gauss you can have. So what is the Earth magnetic field? 10 to the power 10 Tesla field. The contrast.
Right. I think it's around 60,000, is it? Nanoteslas or something, or its magnetic field.
60,000. So it's 10 to the power 10 Tesla field. You see that? So
Yeah, and
way,
that's
way higher.
nanoteslas, I think, is the Earth's magnetic field. It's usually measured in
Yeah.
nanoteslas.
You are talking 10 to the power 20 or whatever.
Yeah,
Different.
it's very ridiculously. Well, so nanotest 60,000. Yeah, anyway, so what a nano is like a millionth
10
of
to the
a
power minus 9, right? 10 to the power minus 9.
nano is it?
Nano. Yeah.
Oh, okay. So
Nanometer is 10 to the power minus 9 meters. Or 1
yeah.
Armstrong. Yeah.
Okay.
1 Armstrong.
And then so
10 Armstrong.
60,000 of those would bring you up kind of 0.6 of a millitesla or something. And so then you got, yeah, it'd be about 13 orders of magnitude or 14.
Yeah.
14 orders of magnitude.
Ridiculously.
Mm.
So they can bend space, definitely. I mean, such level of magnetic field. They can bend space time.
A magnet, isn't it usually the gravitational field that bends the space? I mean, obviously, if you dump enough electromagnetic radiation into a region of space, it's theorized that would cause space-time distortions, but it's never been
warping,
has it? But it
they
should.
can create
Yeah,
warp.
isn't it energy or mass or energy would both work? So if you have a lot of energy, that should bend space, shouldn't it? So you're saying that this 10 to the 10 Tesla field is enough to bend space, you think?
Yeah.
Yeah, why not? Sounds legit. Okay, Rajan, we're going to leave it there. We've been 2 hours and another 1.5 or something.
Yeah, it's a long thing, but I think we covered a lot of different things.
We did, yeah. I hope what I said was useful and.
Yeah, so I'll try to some point I'll try to revise that in some and then present it again. And if you have, but only thing is a documentary movie. I would like to have that or some simulation, but I doubt whether I can do before the conference.
Yeah, fair enough. Well, it's
Yeah.
pretty good in its current state, but if you can improve it, do. That's what I'd say. But,
yeah. So I have something, that's what I want to have some material, upfront, so that even if I don't have emergency, I can use this, and then stop it at the reference point, and then say, okay, just scan and the rest of it is that. And these are our research in progress, things like that. I can leave it at that.
All right.
So just to confirm, because you are the chair, you can always stop that, and then I am chairing yours, so I think it should be fine. We know each other's thing.
Keep an eye
get
on
an idea. Yeah.
Okay.
Sounds good. Thank you very much. Have a nice week, Christopher. Next week we'll see, and I'll try to put it in the WhatsApp about our T-shirt, and then After that, we'll see who picks up. Most likely last law if possible, and
Oh
then
yeah.
we'll see how that goes. Okay, thanks. Good. Thank you.
I think
Mhm.